Hello. Welcome to Astronomy on Tap. Thank you very much. Thanks for coming. My name is Yair, and co-hosting with me this month is Curtis. We are both postdocs at the university here studying astronomy. And Curtis is going to tell you the plan for the evening.
So tonight we're going to start with a talk by Tim Lister. And so he's going to tell us that. And then during the talk and after the talk, you can text your questions to 805-55-AOT-SB. And so after the break, then we'll have a break, and then we'll answer your questions. And then after that, we will do astronomy in the news. And then we'll have another break. And then Kevin Bundy's visiting us from UC Santa Cruz. And again, during his talk and after his talk, text your questions to the same number. And then we'll finish up by answering your questions and doing a raffle.
Right. And people who we select their questions.
Yes. And people who we select their questions, go to the back desk, and we will give you one of these postcards, which is M80, a picture of the galaxy M83 taken with Las Cumbres Observatory telescopes. So those are pretty cool.
Yeah. So before we get started, we wanted to just mention that we've been doing Astronomy on Tap here for over a year now. This is our 12th event. And we just, want to say thank you to all of you who keep coming, and you're the reason we do this. So we really enjoy it, and you guys are a great crowd. And we tell all our speakers, you've never given a talk to a crowd like this. These people are engaged, and they ask excellent questions, and they're super interested. So thank you so much for coming back. And thanks. Yes.
Thank you.
And so we think we're doing pretty well. Here's who you are. We've asked you a few times, who are you coming to Astronomy on Tap? So we span pretty much all ages. We're pretty equal in both genders, which we're pretty happy about. And yeah, and 75% of you come back, which is good. Or 75% of you are here. It's not your first time here, and so we're happy to have new people and people who come back. And we want to ask you this information just based on one event where people answered our questionnaire. And this kind of information is super helpful for getting funding from the city or other kinds of organizations that want to do activities like this for the community. We need to show some information about who actually attends this. So it would be really, really helpful for us if you could fill in our anonymous questionnaire at the end of the evening, just so we can do statistics like this. It's totally anonymous. It'll take you less than 5 minutes. You should have gotten a little business card with a link to that, so you can do it at the end of the evening. You can do it from your phone. And if not, we'll show that link again at the end. And so that would really help us out if you could fill in that questionnaire. And if you want to help us out some more, we'd also be happy to accept your donations at the front desk. And for a $10 donation, you can get an Astronomy on Tap t-shirt. And for $20, you can get one of our posters. These are posters that we made at the observatory with pictures taken from our telescopes. Can't get these anywhere else. And then also, if you just want to say hello at the front desk, and we'll have pens and magnets and other stuff that you can see there. And from the break, we'll have a surprise at the front desk, which we'll reveal later. Okay. So I think we're ready to get started here.
So our first speaker is Tim Lister. He's a staff scientist at Las Cumbres Observatory. And I think his Twitter profile picture just says it all with what he does. Can you guess what he works on? So he's going to tell us a little bit about that coming up. Now, he's also a bit of an electronics enthusiast. And so he's got this lab, and you might think this was at the observatory, but this is actually at his house. And he's just bought his 4th GPS receiver, so apparently he knows where his house is to really, really, really high accuracy, I guess. And he's also quite the grill master, so he's turned his grill into a smoker, and sometimes he comes and shares his creation with the people at the observatory. I don't know how he gets away with it, considering his wife's a vegetarian, but he does anyway. So here's Tim Lister.
Hello, thank you. So this evening I'd like to talk to you about near-Earth objects, or NEOs, and the threat that they can pose towards the Earth. So near-Earth objects are asteroids, so these are chunks of rock and metal that are floating around our solar system, and these can cross the path of the Earth and potentially impact on the Earth. A lot of you know that the dinosaurs are thought to have been wiped out by an asteroid impact about 65 million years ago. So how do we know that this was the case? Are there any more of these things floating around there that could hit the Earth? And what are we sort of doing to find them? Also, I'd like to say a little bit about what studying NEOs can tell us about the formation and the evolution of the solar system. And I'll say a little bit about what other uses we can put NEOs to in the future. So this movie here on the right is a sort of top-down view of the solar system. So this shows all of the main belt asteroids in green. These are orbiting between Mars and Jupiter. But inside of that, you can see red and yellow dots, and these are the near-Earth objects. These are the ones that have been kicked out of the asteroid belt and can come into the inner solar system where the Earth is. And we know of 500,000 or so asteroids now. So how do we know that there's these chunks of rock running around the solar system that are not looking where they're going and running into things? Well, if you look up at the moon, and tonight is a full moon, so this is an experiment you can all do once you leave Astronomy on Tap. If you look up at the moon, and there's this beautiful image here of the near and the far side of the moon, you can see these circular features on the moon, and these are impact craters that are caused by things running into the moon. And these show up even more clearly if you sort of measure the height of the surface of the moon, as we've done in this image on the right, and you can see that these impact craters are sort of depressions in the Earth, in the moon's surface. And in particular, you can see this big purple area at the bottom of the image. This is the so-called South Pole Aiken Basin, and it's one of the largest impact craters we actually know of in the whole solar system. So we know the moon is getting hit, but what about the Earth? I mean, the Earth is a bigger target than the moon, and we're kind of fond of the Earth, you know, we live on it. So it's a little bit harder to find impact craters on the Earth. We have, you know, weather and erosion, which tries to erode craters on the Earth. Also, a lot of the Earth is covered in water or ice, which makes it much more difficult to find craters. But if you look in things like the deserts of Arizona, we can find evidence that there are impact craters here. And so this image here on the left shows Meteor Crater in Arizona. This is a little under a mile across and several hundred feet deep. I mentioned earlier that we think the dinosaurs were wiped out by an asteroid impact. This was a much larger impact, and the crater is over 100 miles across. But despite the size of this, it actually took a long time to find. This is an image of it here on the right, but this was actually found by people doing seismic surveys looking for oil in the Gulf of Mexico. So if we zoom out and look at the Earth as a whole, we can actually find a large number of craters. And as I say, we know there must be more than this because there's, you know, we can't find craters at the bottom of the ocean or under ice or in the middle of jungles or rainforests. And we actually have, you know, evidence that these things do actually run into the Earth, and we have a special guest star here with us tonight. So fresh-ish from outer space is a large chunk of Nicolayan meteorite, and you can go and pet the space rock at the end of the talk. Thank you, Yaya. But it's actually a little worse than this, because a large number of the asteroids don't actually make it to the Earth's surface and cause impact craters. So this map here is a map of over 700 fireballs that have been recorded by US government sensors. What these are is they are basically things that are looking for people doing nuclear testing illegally. And it turns out these are really good for finding large chunks of rock that are coming into the Earth's atmosphere at high speed and exploding, because they're designed to look for explosions. So just to give you an idea of how big a bang these things are, this scale here is in kilotons. So this is thousands of tons of TNT equivalent. So here on the bottom of the scale in blue is 100 tons of TNT, and this is equivalent to 10 of those Moabs, the mother of all bombs, that was recently dropped on Afghanistan. So these are big booms, but they get bigger booms. Towards the top of the scale, we can see the biggest one we sort of know of during here, and we'll talk more about this later, was over 400 kilotons of explosion. So how big are these things that are coming in and causing these explosions? Well, if you look on the internet and Google for asteroid impact, you'll get images that look kind of like this, which is very spectacular looking and also very, very wrong. This is another popular one. So this shows an ocean impact with giant tsunami and huge amounts of material being thrown out. This is also very, very wrong. Nothing this big has hit the Earth since the very early days of the solar system, when the moon was created and those big impact basins we saw on the moon were created. There is nothing this size out there that can hit the Earth anytime soon. So how big are they really? So this is a beautiful image of the Earth taken from space, and on here, to scale, is the size of the asteroid that wiped out the dinosaurs. Can anybody see it? Well, to help you out a bit, we'll zoom in a little bit. How about now? Helpful space arrow. So if we zoom in even further, and this is about as far as we can go, it's up there. It's a couple of pixels on this image, and this was, a huge impact. Happened, these things only happen about every 100 million years, cause a huge amount of devastation. But is there anything out there that runs into us more frequently than this, and what sort of effect would that have? So these are videos taken from people's dash cams as people were driving to work in the early morning in Chelyabinsk in Russia. And what you can see coming in here is one of these fireballs. And you can see these things were brighter than several times brighter than the sun. And certainly make you for an interesting commute on your way into work. So we can see it, streaking in here, and it's exploding in the Earth, in the upper atmosphere, and burning out. But it's not just light that we got from this. So here's people looking at the smoke trail that was left by this object. And that's the blast wave arriving. So this illustrates a really good point about physics, in that the speed of light is not equal to the speed of sound. So the problem with this is, people saw this bright fireball in the sky, they either went to the window or rushed outside, and then 2.5 minutes later the air blast arrived, because it's traveling much, much slower than the light does. And this caused a serious problem. So from studying the footage from these dash cams, we know that this was about a school bus-sized object. It weighed about 10,000 tons, came from the direction of the sun, so we had no warning it was coming, and it exploded at an altitude of about 75,000 feet. Now, the blast was equivalent to like 440,000 tons of TNT, so this is like 30 times the bomb that was dropped on Hiroshima. Fortunately, this object came in about 20 miles south of the city and didn't go directly over the city. But as you can see, and you felt from the air blast, this was a serious deal. And 1,500 people ended up going to hospital, either from blindness caused from the bright flash, or from basically, getting windows or doors in the face when the blast wave arrived. So that's Chelyabinsk. This was caused by an object that's about 50 feet in size. I talked earlier about Meteor Crater. So this was caused by an object that's about 50 meters in size, or about 150 feet across. But what would happen is if we dropped something a little bigger. So there's this really great website called killerasteroids.org, which allows you to drop asteroids of small, medium, or large sizes on any place of your choosing. So in best Hollywood tradition, we're going to drop it on Santa Barbara. So this is about a 275-meter object, so it's about 3 football fields. And this thing is coming into the atmosphere at about 12 miles a second, or about 40,000 miles an hour. So when this thing hits, everything in the middle with that red dot, which is basically all of downtown Santa Barbara, gets vaporized, and we all end up in the side of a 3-mile-across crater. As you go further out, it's less serious. I mean, it'll just demolish buildings or set your clothing on fire or give you really bad burns. And even if you're out as far as Lompoc, which is sort of 50 miles away, the first thing you'll see is a giant fireball that's 10 times brighter than the sun. The next thing that arrives is like a magnitude 6.4 earthquake. And then finally, as we saw in the video, the air blast arrives, and this is like a hurricane force wind that will basically blow out windows and cause a huge amount of devastation. So this is a pretty serious deal. This, would not be a good day out. So how many of these large things of different sizes are there out there, and how many of them have we still got to find? Well, the good news is for the really big things that are bigger than a sort of 1 kilometer, that would basically, cause devastation on a continental or a global scale. There's about 970 of these things, and we've found well over 90% of them. There's not that many of them left to find, and you usually get good warning. As we come down in size to objects that are between 300 meters and 1,000 meters, that would still, devastate the whole of the continental US. There's about 2,000 of these that we're left to find, and these will hit the Earth about every few million years. As we come down again in size to like the one we just dropped on Santa Barbara, hypothetically, that have regional or sort of state effects, here the numbers are not so good. We've found some of these, several thousand of them, but we still think there's over 15,000 of these guys still to find. And as we go down smaller again to the ones that sort of created Meteor Crater or the Chelyabinsk-sized impact, the so-called city killers, the numbers here are very uncertain, but they're basically, there's at least 1 million of these objects still to find. So how do we go about finding these objects, and how do we, hopefully before they find us? Well, on this slide, you are basically looking at 100% of the Earth's protection assets for rocks from space. These 2 telescopes spend most of their all night, every night, surveying the sky, looking for new asteroids. And the number of people that are involved in this search is less than 10% of the number of people in this room. So Hollywood has this funny notion not only about asteroid impacts, but also about how astronomers do work. And if you see telescopes in the movies, they usually involve somebody looking through an eyepiece. These ones here are particularly good because they're all happening in very brightly lit rooms, which is great for trying to find really faint objects. Works really well. So this is what an actual asteroid survey looks like. So this is inside the Catalina Sky Survey's operations center. And this is how most of astronomy is done these days. We write software to control the telescope to scan the sky, and so you can see in the upper right screen, there's an image of the areas of the sky that they're planning to cover. We write more software which controls the camera, takes images, we process those images, and we're looking for new moving objects, and we double check this is working by sort of looking at dots on screens as they move. So once these surveys find a new object, what happens then? Well, the surveys only take about 4 images of a new asteroid, and this is not enough to tell you what type of an NEO it is, what type of orbit it's on, whether it's going to hit the Earth. And so this is where telescopes, such as those of Las Cumbres Observatory, come in. We can take extra images of the asteroid, we can measure where it is, we can find out what type of NEO it is, we can find out where it's going, remove any chance it has of impacting the Earth, and we can also measure how its brightness changes with time, and we can find out how fast the asteroid is rotating. Another thing we'd like to sort of know is how big are the asteroids and what are they made of? I mean, this really helps if you're trying to understand how big a hole it's going to leave. So, unfortunately, in visible light, like our telescopes work in, we can't tell the difference between small asteroids that are very reflective, like chalk, or much bigger asteroids that are much darker, like a charcoal barbecue briquette. But what we can do is by studying these objects in the infrared, and Amy Mines, the next speaker, will say more about this as she works a lot on this. We can get a direct idea about how big these objects actually are and what they're made out of. The other thing we can actually do is we can actually bounce radar off them and take pictures of asteroids. So the dish here on the left is the 70-meter antenna at Goldstone in the Mojave Desert, not far from here. And they can actually send radar out and take images and make movies of the asteroid. And so on the right here is a near-Earth object which is called 2014 JO25, which is not particularly catchy. This had a really close pass to the Earth on April the 19th. It was in the news, and I think we're talking more about it later. This is about a 0.9-mile across space peanut. You know, this is a thing about the size of the airport or downtown Goleta. We can see it's rotating. So once we know where the object is and what it's sort of made out of, we can potentially go and make use of them. So a lot of them are made out of rock, but also a lot of them are made out of metal. And so people have done sort of some calculations, like for this particular asteroid, which is about 2 kilometers across, it's mostly full of nickel iron, but also platinum and a whole bunch of other materials that are very useful on Earth. And if you work out the value of this, it's sort of like $87 trillion, or several times the US debt. Another useful thing you can get out of asteroids is water. I mean, water is incredibly useful. I mean, you can obviously drink it. You can give it to crops to, grow your space potatoes. You can use it as a radiation shield. The other thing you can do is actually split it up into its original hydrogen and oxygen, and you can use that as rocket fuel. And you can use that to refuel your spacecraft as you go out to other parts of the solar system. So I'm trying not to end on a downer, but this big table here is basically your chances of dying globally averaged over many years due to various things. So asteroids are more dangerous than shark attacks, but they're a lot less dangerous than a whole bunch of other things that we should be worrying about. Now, I should point out that 91 people are not dying every year because they're getting hit on the head by asteroids. That's not the way this works. Nobody dies from an asteroid for 999 years, and then one arrives and tens of thousands of people die. So this is a very different kind of risk than we're used to dealing with, and it's difficult to deal with and wrap your heads around. But we have actually reduced the risk of death by asteroid considerably. Since we started looking for NEOs, the average death rate per asteroid from asteroids has come down from like 1,200 down to about 91. You're quite welcome. And further study of NEOs not only help us find more of them, understand the risk, and eliminate the risk, because once we know where they are, we know they're not going to hit us, or we could do something about it. And it also helps increase our understanding of how the solar system formed, how the NEOs evolved throughout the solar system, and also they will provide us with destinations and sources for raw material as we go explore the rest of the solar system. And so with that, I'd like to thank you very much.
Thank you, Tim. Yep, Tim's expression is the expression he has on his face in the morning is the one we all look at when we come to work at the observatory, just to make sure he doesn't look too worried. Everything's fine.
If you see me running, try to keep up.
Yes, yes. Don't, yeah. We was mentioned the barbecues before. Dreading the day he'll come with like a huge feast and run away. We know it's not a good sign. So thank you for those who've already started sending questions. That's great. Please keep that up. We'll put up the number here in a second. I just want to say that if you want to hear more asteroid stuff, we will have another asteroid astronomer next week. So not here at Matrix, but at the Center Stage Theater, and we'll tell you those details again, but just keep that in mind. There'll be more asteroid stuff next week. And we're going to take a short break, and in the meantime, please text your questions to 805-55-AOTSB. Just type in the letters. And we're going to take our space rock here, which is really heavier than it looks, okay? Really, you should try and lift this thing. It'll be on our front desk, so if you want to see that and see what it feels like and what it weighs like, please visit our front desk. And so we're going to take a 5-minute break, and we'll take your questions after that. Thank you very much. We got some really excellent questions. Thank you all for sending them. Except you, Andy. Stop trolling us with your question. One day, we're going to reveal all the questions that were not chosen. Okay, so let's get started here. Let's see. Yes. So there was one question, which was, when you see one of these craters, do you also find the asteroid that made it? So that's actually a better version of the question I had heard once, is how amazing is it that these asteroids always fall right into these craters?
So that depends a lot on what the asteroid is made out of. So a lot of the asteroids are made out of rock, and they're not always necessarily held together very well. And those ones usually break up and burst in the air, and so those will not necessarily form a crater. Things like, so Meteor Crater was formed by an iron-nickel meteorite, like the space rock we have here, and those things are far more likely to survive the entry sort of through and not get vaporized when they actually hit the Earth, so you usually do find those in the crater.
And so this is a related question. Is the size before it enters the atmosphere the same as the size after it hits, if it does make it to the ground?
No, the size when it's out in space is much larger than when it hits the Earth's atmosphere. These things are coming into the Earth's atmosphere at really ridiculous speeds, up to 40 or 50 miles a second, and they're slamming into the atmosphere, and this causes huge amounts of shock and breaks most of them up. And this is what you saw in the video of the Chelyabinsk one. You could see a couple of flashes as bits of the asteroid were breaking up. So
yeah.
Go on.
Well, there was a related question. You mentioned the velocities. Are they all coming at the same velocity, or what kind of numbers are we talking about?
So the velocities vary quite a bit. So at the low speed, it's about 11 kilometers a second. Comets, which make up less than 10% of the near-Earth population, those, because they're usually coming from further out, those can actually hit with much higher velocities. So those can be up to 60 or 70 kilometers a second.
There's another question. How did that little asteroid kill all the dinosaurs? What was the actual cause of death from that one asteroid?
Well, this depends on your definition of little. We think it was about 10 kilometers across. So that's a pretty huge chunk of rock weighing trillions of tons. When something like that sort of hits, a huge amount of the asteroid is vaporized, and also a huge amount of the thing it hits also gets vaporized. And all of this material gets thrown up into the Earth's atmosphere. And this basically will block out the sun. So you can just end up throwing all of this rock, like we see with volcanoes, but on a much, much bigger scale. So all of this material goes up into the Earth's atmosphere, and it can stay there for years or decades, and it will basically block out the sun. Photosynthesis stops, the plants all die, and the food chain basically gets dynamited at the bottom.
A question that came up a lot is, you mentioned like we still have the number of asteroids to find at different sizes. How do we know how many are left to find? How do we know what the total number is supposed to be?
So I talked earlier about the sort of the surveys that are out there trying to find the asteroids, and so what we can do is by looking at the fraction of asteroids of a particular size that the surveys find, we can make estimates about how many they wouldn't find, and so this helps us make an estimate on how many asteroids are still out there. Also, at the very, very small size, like the fireball data, so these are very small things coming into the atmosphere. They're only a few meters across. And these tell us how many objects there are at the very small scale. And then we can effectively draw a line from the big ones that we know that are being found by the surveys through to the fireballs that are impacting on the Earth's atmosphere. And then we can make estimates for a given size about how many there are out there.
There was also a question about our space rock, asking what big a crater would that make. So maybe we should clarify where that, or what that rock actually is. It's a piece of a larger one.
So this is, so it's a nickel-iron meteorite. It's part of a much larger piece. We're not actually sure which one it's part of, but it's most likely part of a famous meteorite called the Campo del Cielo. This is one of the biggest, so this hit in Argentina. They found over 100 tons of this meteorite in various sizes.
Okay. One last question that also came up a lot is if we did find an asteroid that was headed towards Earth, and actually I wanted to point out in that context, you showed the image of, you can see the asteroid moving in the image, and that's how we know it's an asteroid, but is it true that the one that will be heading straight for us is not going to be moving in the image, is it?
Yeah, this is...
Maybe I don't want to know the answer to this question.
This can be a problem for things that are very close to us, then they don't appear to be moving very fast until they get very close, and then they start moving really fast. This is part of the reason why we need additional information, because when you see it moving on there, you don't have a good idea of the distance, and you can't really tell, what sort of line of sight it's coming towards us, and this is one of the reasons why we take more data with things like LCO.
Okay, and then the question that many people ask is, say we do see one and it is coming towards us, what can we do about it?
Right. So providing we have plenty of warning, we actually have a fair number of options, and I've got a couple of sort of slides that outline some of the things that we do. Next one. So these are the sort of the four main deflection options. The important thing is we're trying to find these well in advance of when they're going to impact. And if we can do this, then you don't actually need to impart much energy to them to actually push them off course and make them miss. The animation that I showed at the start is sort of very misleading. It looks like there's this giant swarm of asteroids that are, whizzing past the Earth, and, why aren't we getting hit every day? But, space is a really big place. The Earth is actually a pretty small target. So one of the things that we can sort of do is we can use what's called a kinetic impactor, and this is basically a fancy term for smacking it really hard with something heavy. So we've done this to comets. There was a mission called Deep Impact, which crashed a projectile. It was a sort of 20-kilo chunk of copper into the comet, and we can do that, and there's a proposed mission to help examine how well this will work and monitor the effect. The other thing we can actually do is this thing called a gravity tug, where you basically just park a spacecraft next to the asteroid. The asteroid attracts the spacecraft, but the spacecraft also attracts the asteroid, and that will actually gradually tug it off course to the point where it will miss the Earth. Another thing we can do is what's called a mass driver, and particularly if we're going to get into things like asteroid mining, this is something that we might well be developing. So you can land the spacecraft on it, you can basically mine and you either refine it and turn it into fuel and burn it, or you just literally fling rocks off the asteroid. Newton's law of every reaction has an equal and opposite reaction. And finally, we have the sort of, the Bruce Willis Armageddon nuke it in orbit. This does work. You're much better off doing it as what's called a standoff nuclear blast. Drilling into the thing really doesn't make any difference and runs the risk that you're going to fracture it and you turn from one large asteroid into a whole bunch of little ones. But this is a good option, particularly for things that we don't necessarily have a lot of sort of warning about. You can do a standoff blast. But we need to do a lot more sort of research to understand what asteroids are made of so we know how effective these sort of things would be.
Okay, thank you very much, Tim.
Thank you.
So, where did this come from? Hang on. Okay, so we're going to move on to our next part of the evening here, which is our astronomy in the news section. So there's a lot of astronomy in the news lately, and in this section we tell you about the stories that came out in the press and whether they got it right or not, or what actually is going on. So the first story actually Tim mentioned was this badly named asteroid 2014 JO25 that passed close to Earth a couple weeks ago on April 19th. It passed about 1 million miles from Earth. It is actually one of the largest things to have passed that close to Earth recently. So originally it was thought that it was about 2,000 feet across, but as Tim mentioned, when it got really close, we could point a radar at it and actually get radar imaging of it. So that's one of the radars we pointed at it, the Arecibo dish, which is pretty big. There's a car there for scale, just so you see how big that thing is. So that was, we're beaming radio pulses at it. And this is what we got. On the right here is a radar image of this asteroid. You can see it's actually two, looks like, Tim called it a peanut. I think it actually kind of looks like a rubber duck. See, it has a little tail. But it's actually kind of two asteroids connected together and now rotating as one object. So it actually is twice as big as we thought it was. It's about 1 mile across. And it spins every 4.5 hours. And so that's part of the data we can get when these things pass close. And the other thing, as Tim mentioned, is from our own observatory. We can see how bright the asteroid looks with time. And you can see it gets brighter and fainter. And that's because it has this irregular shape. And it's rotating. And so this, together with the radar data, can give you a good idea of what the asteroid looks like, what its shape is, how it's moving, and a little bit of what its reflective surface is, based on how much light we get. So I think it's a pretty neat way to study these things, and good that it was 1 million miles away. And now we know what it looks like.
And so Enceladus has been in the news quite a bit lately. And so Enceladus, the moon you think about so little that you didn't realize this is not Enceladus. This is Hoth from The Empire Strikes Back. This is Enceladus. So this is a really spectacular picture taken with the Cassini mission, which we're going to tell you a little bit more about in just a minute. And so the headlines say something about conditions for life found on Enceladus. So Newsweek, usually a reasonably reputable news source, tweeted this, and it's impossible to read here, and it says, I can't even read it there.
It says, "Are you sitting down? NASA has found signs of life on a Saturnian moon."
And no. Just no. How about the Washington Post? Okay, so NASA finds ingredients for life spewing out of Saturn's icy moon Enceladus. Okay, the title's a little better, but their front page image is not great, right? It's not Enceladus. It's not even Saturn, for that matter. It's not even a moon. That's Jupiter. And that's definitely not like ingredients for life spewing out of here. So, not so much. So what they actually found is pretty interesting, but they found molecular hydrogen in the moon of Enceladus. Now, would you click on that? Is that an exciting link? Probably not. But let me tell you, it's actually a lot more interesting than you might first expect. And the reason it's interesting is where they found it. So this is another picture of Enceladus. Now, I put the moon to scale, and this is about 300 miles across. So the whole moon is only 300 miles across. This is a picture taken with the Cassini satellite where the sun is behind it, so it's backlit by the sun. This is basically totality for an eclipse like Andy told you about last month, right? And there's this little patch here that goes below it. That's a geyser. So that is a geyser that is shooting 30 miles into the air. 450 pounds of water is getting pushed out. every second to a speed of 1,350 miles per hour. This is incredible. It's ejecting so much material, and because it's water, it's really reflective. And so it's produced a known ring of Saturn called the E ring. And so Enceladus is this little dot in the center, and all of this material forms another ring of Saturn, and it's kind of like a comet tail. So where does hydrogen fit into this whole thing? So they flew the Cassini spacecraft through that plume and actually collected some of the molecules, some of the particles that were coming out of those geysers to see what they're made of. It's kind of amazing that Cassini had that equipment on there. So they already had a mass spectrometer on there for measuring the atmosphere of Saturn, and so it was just good fortune that they were able to do this. Normally, if you wanted to figure out what was on Enceladus, you'd have to go drill down through the ice and figure out what this. Now the geysers spew all that stuff into outer space, and so we can just pick it up for free. So the interesting new result is that there's hydrogen in this gas. It's not just water, so hydrogen like the Hindenburg. Now, this is interesting for a couple of reasons, but the main one is that you don't expect to find that anywhere near where there's a lot of water because it's going to react so quickly. And the place we see this on Earth is at the ocean floor. So this is a picture from Earth, not from Enceladus. That would be an awesome picture to get from Enceladus. But this is a hydrothermal vent on the Earth, and some of the material that comes out of here is pure hydrogen. And so the idea is that something similar is happening in the bottom of an ocean on Enceladus. So how does life fit into this? Well, on Earth, there's a ton of little microbes that live on the and feed and basically breathe the hydrogen out of these geothermal vents. And so the idea is that if this hydrogen exists, maybe those same type of microbes could exist on Enceladus. So normally we talk about when news gets it wrong, but actually this one got it pretty much right. It's a picture of Enceladus, not Jupiter. It's a good start. But then they say, new study of Saturn's moons, Enceladus, suggests that it could host life. I couldn't have said it better myself.
Okay. So Curtis mentioned this incredible data came from the Cassini spacecraft. So I want to tell you a little bit about Cassini because it launched in 1997, 20 years ago, and it took 7 years to get to Saturn in a pretty incredible trajectory. It got launched from Earth, flew past Venus, then flew past Earth again, then flew past Venus again. So this is all gravity assist flybys that allow the spacecraft to use the gravity of a planet to like slingshot it further out, and then did the same thing with Jupiter, and eventually arriving at Saturn in 2004, and became the first spacecraft that ever orbited Saturn. And so it took some spectacular images. It's been taking. This is actually on the way to Saturn. This is Jupiter. So this is Jupiter's moon Io and Jupiter in the background. This is an image that the spacecraft took as it was passing Jupiter on the way to Saturn and then eventually arriving in Saturn. This is a real image that it took. Everything I'm going to show you here are real images. One of the other extraordinary things, it took a smaller probe with it called the Huygens probe, which had actually landed on one of Saturn's moons called Titan. So we got pictures of this probe as it was landing on the surface, and it actually landed on the surface of Titan and sent in these pictures. Through this mission, we've also learned a lot about Saturn's rings and how they work. This is another real image of Saturn's rings. We've learned a lot about Saturn's moons. This is a moon called Hyperion. Again, a real image. Actually, Cassini discovered 7 new moons of Saturn since it's been there. Here's another amazing picture of the rings and of Saturn. Here's the thing at the top. There is a huge storm on Saturn that the spacecraft caught. Here is the moon Mimas or the Death Star. I always get these confused. I think it's Mimas. And here is another great image just to illustrate actually how thin the rings are. So you see their shadow on Saturn in the background, but this is really edge on. You see just how thin the rings actually are. It's another picture of Enceladus, which we've seen. And here's one of my favorites. This is Saturn, viewed backlit by the sun on the other side. And yeah, this is quite spectacular. Thank you. I didn't take it, but this image is pretty spectacular also because it's hard to see, but there's some little dots here. And some of them are the moons of Saturn. There's this, zoom in here, that little blue dot is actually pretty interesting because that's us. So you actually have the Earth in this image as well. I think NASA, when they took this image, told everyone on Earth to smile, which is hard to tell if we caught it, but yeah, that's Earth. And then some of the other spectacular things, you might notice there's a hexagon on the North Pole of Saturn, and we don't quite understand how you get a hexagon from stuff moving around on a planet, but that happened, so it's also investigating that. And so it's been a hugely successful mission. It's been going on for 14 years, 13 years since it got to Saturn, and but Curtis is going to tell you it's about to end.
Yeah, so it's been just wildly successful. I was talking to Tim, and he said it was something like 1,700 PhDs have come out of data from the Cassini probe. So there's a lot of work that's been done. But it's been 20 years, and it's starting to run out of fuel. And so we've got a problem now. What do we do with this mission after it's been alive for so long? And so instead of worrying about just like letting it run out of gas and then crash into wherever it may, so perhaps Enceladus, and you don't want to contaminate any of the moons. And so NASA's decided that we're going to crash the Cassini probe into the atmosphere of Saturn, and it's going to go out with a bang, and it's going to burn up in the atmosphere.
We should say this is more than just, it'll be pretty cool having it crash into Saturn. It's also, as Curtis said, there might be life on Enceladus, and we don't want it to crash there, because then maybe in the future, if we do detect life, we won't know if it was there initially or if we brought it there on Cassini somehow. And so there's this agreement among nations who send spacecraft into space. You have to make sure they don't crash into a place that might have life in order to not contaminate it, so we would know if that was there intrinsically or not. So that's why they want to crash it into Saturn itself.
But before we do, it's going to have one last hurrah, and we're going to actually plunge through, they're going to plunge the satellite through the rings between Saturn and its rings to see what we can do and to see what we can learn. Now, this is just an animation. We actually don't do that. I'm going to show you real data in just a second. So, and not only are they going to crash it and plunge through the rings, between the rings and the actual planet itself, once, they're going to do it 21 times over the next several months. And so it's going to keep going round and round and round until finally in September, they're going to crash it into the atmosphere of Saturn. And they're going to keep the instruments on as long as they can and try and beam as much information about the atmosphere back as they possibly can. All right, we don't have to watch all 21. But we've already got the first one, and actually we've already got the first two. So this is data from the first plunge that's coming through. So we're starting above Saturn, and we're going to dive between the rings of Saturn. And this little red dot on the right-hand side shows what part of Saturn Cassini was looking at. And then on the left, it's the actual data from the dive. Now, I want to just mention, first of all, this is a hurricane on the left side that you're seeing. Just for some scale, this is 1,200 miles across. And so this is about the size of the West Coast. Pretty big storm. So then it's going to dive down, and we see all kinds of interesting features. So there's going to be clouds and storms, winds and currents in the atmosphere. There's going to be gaps in the atmosphere, different layers of the atmosphere that it sees. And this data alone is going to keep scientists busy for years to come. And I told you, so we've made 2 dives so far, and actually the third dive happened, I think, yesterday. And so they're actually just downloading the data for that right now. We don't have that yet. So the second time, we turned on a different instrument. This was released just a few days ago. And they're trying to make images of the rings. They're trying to see if there's anything between the rings and the planet itself. Is that just empty space, or do the rings extend all the way into the atmosphere of Saturn? So on the left, you have what it looks like when you go through the outer edge of the ring. And so you've got the dive going down, and then you've got the number of particles, so basically the density to the right. And so you can make an effective image of what the ring looks like. And so when you dive through a ring, you expect a bump that looks like a ring. Now, or a slice through a ring. Now, when they did this on the other side between the planet and the ring, They got nothing. So the only thing is maybe this like little patch of turbulence. I hope they were all wearing their seatbelts, right? But there's just nothing there. And so they've actually started calling this the Big Empty. And so we're still continuing to learn fascinating things about Saturn, even though it's not that far away from us compared to a lot of things that we've talked about. But the Cassini mission, even its last days, is telling us a huge amount about our own solar system.
Okay, so we will definitely keep you guys posted as this grand finale of Cassini happens in September. For our next news story, something a little closer to Earth, this group called the Alberta Aurora Chasers in Canada discovered a new type of light in the sky, which you see in the image on the left, and they called it Steve. They saw a new light, they called it Steve. And so the question is, what is Steve? It doesn't look like other aurora lights. And so, first of all, what is an aurora? So you need three things to make an aurora. I'm sure most of you have heard of aurora or northern lights or southern lights. Here's how it works normally. You have the sun. The sun is emitting not just light, but also stuff. Stuff is coming off the sun. Electrons and protons, typically. So that's flowing towards Earth. Okay, that's the first ingredient. Second thing is Earth has a magnetic field. The same thing that directs your compass needle is felt out in space as well, and these particles feel it. And it's a good thing because it deflects most of these particles from the sun away from the Earth, which is good. This protects us from these particles. But you'll notice the shape of the magnetic field kind of funnels some of the particles into the poles. So some of the stuff coming out of the sun, most of it gets deflected. Some of it goes down along these magnetic field lines into the poles. And then the third ingredient is when they hit the atmosphere and they light up the atmosphere in these spectacular colors. So what does that look like? Here's an example. So I actually wanted to see this for myself. So a month and a half ago, I went up to Alaska, where it was 0 degrees Fahrenheit, and I was terrified of, like, how does that even work? But it was worth it. It was worth it, because you get to see these kinds of things. So this is the aurora. It almost looks like a painting on the atmosphere, right? These are particles from the sun hitting the Earth's atmosphere and being deflected by the Earth's magnetic fields. Here's another example. It was a beautiful, clear night, and the aurora was amazing. So I recommend everyone go do this, even though it's really cold. You see different colors. Different colors come from different elements in the atmosphere that the particles are hitting. If they hit oxygen, you get this greenish thing. If they hit nitrogen, you get a purplish glow. And it's really something you need to see for yourself. One of the things that doesn't come through in the pictures is that this stuff actually moves around. This is a time lapse. I took a few minutes of just the aurora dancing around, and it's really hypnotizing. I really recommend going to see it. And so maybe now you can understand a little bit why there are people who are aurora chasers. This does get pretty addicting. And so these aurora chasers found this kind of thing, which you see looks different than the ones I was showing you. And they showed this to an aurora scientist. They thought this was just some other aurora activity and said, no, that can't be just a regular aurora activity. It's something else. And he did what typical aurora scientists would do when you get shown an image like this. He took his constellation of satellites that are operated by the European Space Agencies. These satellites measure the Earth's magnetic field. And with collaboration with these aurora chasers who were able to tell him from the ground where are they seeing Steve happen, he was able to get one of the satellites to just fly through Steve and get some measurements. So some of the things they learned is that these lights are 200 miles high. They're about 5,000 degrees Fahrenheit hotter than the surrounding atmosphere. The stream is about 15 miles wide and moving at a crazy 13,000 miles per hour. So this is what they measured. Still not exactly clear what it is exactly and if it's related to the aurora or not, but just being able to measure it for the first time is a great first step. I think it's a great example of collaboration between amateur astronomers and professional astronomers. There would have been no way to nail this down before. So they're still trying to figure out what it is, but at least now we have some data on it. And if you're wondering why they called it Steve, here's the actual reason.
I would be a lot less afraid of it if I just knew what it was called.
Let's call it Steve.
Steve?
It's a pretty name.
Steve sounds nice.
Yeah, I'm a lot less scared of Steve.
Yeah, that's why. It's from this movie, which is called
Over the
Over
Hedge.
the Hedge. Thank you. Yes. Over the Hedge. That's why they called it Steve. We'll see once, it might get a scientific name later. I don't know. It might stick with Steve. We'll see. But yeah, that's our news for today. Thank you.
Thanks.
We'll take another short break, and we'll be back with our second presentation of the evening about Undead Galaxies, so stick around. Okay, we're ready to get started with our second presentation of the evening. Just a reminder, if we picked your question, go see us at the front desk to get your M83 postcard, if we picked your question. So our next speaker is Kevin Bundy. It's really great to have him here. He's from UC Santa Cruz, and he's in town visiting, so we immediately snatched him up for an Astronomy on Tap. Kevin lived in Japan for 5 years as part of his job, and he also enjoys rock climbing, so here he is on a rock, and here he is on another rock. Another interesting thing about Kevin is that he got married in Hawaii during the Venus transit of the sun. So Venus transit of the sun, the next one's going to be in like 100 years. So that was a pretty rare event to have during your wedding. I hear they had the transit being projected throughout the ceremony. It takes like an hour to Venus to cross the sun. So that was pretty neat. And this man here on the right is Kevin's thesis advisor, I think, Richard Ellis, who is commander of the British Empire, which is apparently a title you can get if you're a distinguished Englishman. Just before Lord, I think, is commander of the British Empire, which he is. So he was explaining about the history of the Venus transit, if I'm not mistaken, during the wedding. So yeah, that's pretty unique. Okay, so let's welcome Kevin.
All right, thanks very much. How's everyone doing? Good. So I think it's fair to say that most of us, if we're honest, are maybe a little bit concerned about the undead, right? We've got zombie movies, we've got vampire movies, we've got Game of Thrones. So this is a White Walker from Game of Thrones, and we've learned recently that all these guys have to do is just lift their arms, and they can raise entire armies of the undead. And we know that those armies are going to march south, and they're going to attack the humans. Maybe they've already done that. I'm a little bit behind. But anyway, I think a little bit of concern is warranted here. But you may not realize that there's something else to be worried about, and that's undead galaxies. So you may not even know that galaxies die, but in a real sense, they do. And astronomers have been wondering for a long time why it is that they stay dead. How come they don't rejuvenate? How come they don't come back to life? And so this is a question I want to talk about today, and it's important because if we ever do get attacked by an army of undead galaxies, we should be prepared. We should know how to fight back. And I want to talk a little bit about some new observations that I think are giving us an important clue. And the answer seems to be something to do with the power of black holes, supermassive black holes, in the center of these galaxies. So to get us started, let's kind of orient ourselves. I want to just point out that we're living in a galaxy. It's called the Milky Way. And a galaxy is like 100 billion stars, of which our sun is just one. So this is an artist's conception of the Milky Way. We don't actually have the ability to take an image because we're embedded inside it. It would be like trying to take a picture of your house when you're stuck inside your bedroom. But this seems to be pretty accurate, and we know a lot about the Milky Way. We know that over the history of the universe, it was mostly forming stars, and that's what galaxies do. They take cold gas, and they provide an environment for that gas to cool. This is mainly hydrogen gas. to cool and to form stars. And that's how you get 100 billion stars by today. So you can think of galaxies as really machines for turning gas into stars. So the Milky Way is not alone, and I want to show this visualization of the nearby universe. So what we're doing here is we're flying through the space around us filled with other galaxies. Each of these galaxy systems, again, 10 or 100 billion stars inside them. And every galaxy here is an actual observation that was made with the Sloan Digital Sky Survey about 10 years ago. So these were all cataloged objects, and we've mapped out their location in 3D space, and so we're sort of flying through that. It's kind of like not Google Earth, but maybe Google Space, if you like. And the thing I want you to notice, if you can, on the screen, is that, especially as you get closer, you can see there's sort of two different types of galaxies. So a lot of them, most of them, are sort of bluish in color. Those are the ones that are still actively forming stars. But you might be able to see some kind of yellowish ones. Those are the dead galaxies. And that's what I want to focus on tonight. So this dichotomy between living and dead galaxies is really fundamental to the galaxy population today. Let me come back to the Milky Way. I mentioned that it's still forming stars. It's not doing so at a very impressive rate. We form stars at something like 2 or 3 new ones per year. And in fact, we know from other observations of the Milky Way that most likely we're not going to be lasting too long in terms of star formation. The Milky Way itself is going to die in about 1 billion years or so. So this maybe brings things a little closer to home, because now you might be a bit more concerned about your own galaxy rising from the dead. Let me show you some other examples of star-forming galaxies. So these systems tend to be disk-like. They have the nice spiral arms that you're used to seeing and other features in them, and they tend to be a little bit blue in their color. And that's just because there's new stars forming all the time, and when that happens, you get these hot young stars that burn very brightly for a short time and die out, but then they're replaced by other ones. So they tend to be a little bit on the blue side. Now I want to show you some images of galaxies that are dead. And you can see that they tend to be more yellow in color. They are round and smooth. They don't have that spiral structure anymore. And in fact, we refer to them as red and dead. I know they're not actually red in the image, but it's like the hair of a redhead is not exactly red. There's a red hue, okay? And that's because those young stars that are so hot and so blue have long since died out in the dead galaxies. We're just left with these old stars. They're colder, they're more garden variety, and nothing much is happening in these systems. Okay, so again, young, youthful star-forming galaxies on the left, no more star formation, red and dead galaxies on the right. The question for tonight is why those dead galaxies no longer form stars, why they are never in a position to rejuvenate star formation, why they never raise from the dead. And to illustrate that, I'm showing a movie from a simulation of how galaxies evolve and form over time. And you're looking at a handful of galaxies that are in close proximity, and they're interacting with each other. The thing that I want to point out is the difference between the left and the right. So on the left, in this simulation, we're just showing the stars. This is the closest thing to what you would see of an image of these galaxies. On the right-hand side, though, you're seeing the gas. And in practice, in real observations, the gas is very hard to see. In a simulation, it's easy. And the thing to notice is that stars are relatively, I'm losing my mic. The stars are relatively confined, but this hydrogen gas is sort of everywhere. So after the galaxies die, there's still plenty of gas around. And the question is, why doesn't that gas fall into the dead galaxies and start star formation all over again? It's kind of like that cold gas is like the presence of the White Walkers out in space. And why aren't they able to raise the galaxies back to life? So where are the undead galaxy armies? And an astronomer would say, what keeps galaxies from forming stars after they die? Well, to address this, I want to talk about a new survey that we're doing. This is called MANGA, and MANGA stands for Mapping Nearby Galaxies at Apache Point Observatory. And it's one of the current generations of the Sloan Digital Sky Survey. You're looking at the Sloan telescope on the left-hand side. This is the telescope that provided that initial catalog of galaxies that we were flying through earlier in the talk. So this is a new instrument on this telescope that's been around. I want to describe why this new approach is interesting. So let me play this movie a little bit again here. These are all galaxies that were measured by the original Sloan survey. There's like 1 million of them. So how is it that we were able to get all of these observations? And the technology that we used is fiber optics. So we put optical fibers on each of these target galaxies, and that allowed us to collect their light, feed it to a spectrograph, disperse it into the spectrum, the rainbow if you like, and from that figure out their location in space and other information about them. And literally, these are cables of fibers. It may be similar to optical fiber in your home if you're lucky enough to have very fast internet. This is amazing stuff because it directs light through the cables and allows you to put it wherever you like. So you can see a movie there of one of the technicians, and she's plugging 1,000 different fibers into a plate that's going to go onto the telescope. When that telescope points in a specific part of the sky, the fibers will locate on the objects that are targeted in that particular area, and we'll get the information that we need for each of them. So it's really an impressive technology. But there's a problem. And the problem is that we've only put one fiber on every galaxy. In fact, if we really want to understand how galaxies work, we have to account for the fact that they're much more complicated and that a single measurement is not going to tell you everything that you would like to know. So what we're doing in MANGA is we're taking those fibers and we're bundling them together into sets, into hexagonal bundles of fibers, and we're putting those on our target galaxies. And that allows us to collect this valuable information across the face of every galaxy. We're not doing this for just one galaxy at a time. We've got 17 different bundles that we can put down. You can see a schematic. They have different sizes because galaxies are different sizes on the sky. And this is what you need to be able to conduct a really impressive survey. So what we're trying to do is map the internal structure of 10,000 galaxies over a 6-year survey, and we're about halfway through. So at the bottom there, you can see the first 17 galaxies that we collected. Okay, so let me come back to the story about these dead galaxies, because this MANGA data has given us some new insights. So I want to show you right now my favorite dead galaxy. Here it is. And let me describe what you're looking at. So in the background, there's a black and white image of the sky. And the bright spots here are stars that are in the Milky Way. They're just kind of foreground stars, so you can forget about those. Then what I've done is I've superimposed a color image where this red and dead galaxy is. And you can see the purple hexagon, which shows you the footprint for the MANGA observations. What's really nice about this particular galaxy is that it has a little companion. It's got a little friend. And it's quite a bit smaller, but it also has MANGA data. And we know that that smaller companion galaxy is actually forming stars at a pretty good clip. And that means that there's a lot of gas in the system. And hopefully you can see from the background image that there's this bridge. There's sort of a connection between these two systems. And that tells us that material from the smaller galaxy is being conveyed and deposited into the larger one, into the dead galaxy. So this is like finding a system where, the White Walker is standing above the red and dead galaxy and lifting their arms and chanting or whatever it is that they do, and you would expect star formation to start again in this red and dead galaxy, for it to rise up. But we don't see that. We don't see any evidence for star formation in this system at all. So what's going on? Well, what we think is happening is that inside these galaxies, there's something that we call red geysers. So we heard about geysers earlier in the night. We're using this term very loosely. What we mean is that we think that there is energy, superheated gas, not necessarily water, coming out of the centers of these galaxies, and that's actually impacting the surroundings and keeping gas from cooling and forming more stars. Let me show you why we think that is. That's not what I expected to happen. Let me keep it a secret. You can come talk to me after and I'll tell you. There we go. Okay, so again, we're looking at an image of this particular system on the right. Now I want to show you some of the new manga data that we have. Let me focus first on the left-hand image. And this is what manga is telling us about the hot gas in this particular galaxy. And when we saw this, we got very excited because you notice that it has this kind of filamentary structure, and it seems to be sort of emanating from the center of the galaxy. You can see this in other examples, and we immediately thought that this had something to do with the black hole living at the center of this galaxy. And it's pretty commonly believed now that most galaxies, especially at these masses, have supermassive black holes living at their center. And you may know that black holes not only suck, they blow. And so what we think we're seeing here is an outflow, superheated gas that's coming out of the galaxy. And to prove that, we had to look at the gas velocity field. So I want to show you that on the right-hand side. So here the colors are telling you about the line of sight projected velocity that we're measuring. It's almost like we're looking into the 3D structure of this galaxy. Red means gas is moving away from you. Blue means gas is moving towards you. Really, the only way to fit that kind of velocity field is with a model where the gas is sort of being ejected out of the black hole. So here again is a simulation, but it kind of conveys what we think is going on in these systems. So you can see how there's this superheated material that is emerging from the black hole. This is really interesting because the energy contained in this material is sufficient to affect the colder gas that might otherwise come in and form stars. So if you have this phenomenon going on, this may be the answer. This may be why the galaxy is able to stay dead and never comes back to life. Okay, so let me just go over the story one more time. So we found this really interesting system, 2 galaxies. We know the smaller one has gas. It seems to be donating this material to the red and dead galaxy. That should lead to more star formation. That should raise it from the dead, but we don't see any evidence for that. And instead, what we think is going on is that there's this red geyser phenomenon, this superheated outflow of material in the black hole of the red and dead galaxy, which impacts the colder gas, keeps it hot, keeps it from forming stars. So that would be pretty interesting if it was just one system, but what we're really excited about is the fact that because of our large sample in the manga data, we found many other examples of this phenomenon. It seems to be quite common among red and dead galaxies. And so that is really interesting because it suggests that it could play a major role in keeping dead galaxies dead. So if you'll let me run the metaphor into the ground, in a sense, what we found here is dragon fire, right? Because you know the dragon fire is going to affect those White Walkers. You just know that that's going to happen. So we found the dragon fire, these red geysers in the center of these galaxies, and we think that that is what keeps the evil forces at bay, keeps star formation from occurring in dead galaxies. So let me just wrap up. What I've talked about today is some evidence that these black hole outflows, these so-called red geysers, are actually quite common. And that could be very exciting because they seem to have enough power to prevent star formation from occurring in galaxies that have turned off, that are already red and dead. And this could be quite important because it would allow these dead galaxies to rest in peace. So let me stop there. Thank you.
Thank you very much. We'd like to remind you to keep texting your questions to 80555 AOTSB. Thank you for the great questions we've gotten so far. Again, not you, Andy. Are you using other people's phones to text us questions now? Yes. Okay. While you text your final questions here for Kevin, we'd just like to remind you one more time that next week we'll have a guest speaker, Amy Mainzer from JPL, NASA's Jet Propulsion Laboratory. She'll be giving a talk about asteroids at the Center Stage Theater. That'll be next week. Wednesday, 6:30 is when we open. Talk starts at 7. This is free, so you don't need to make a reservation. Just show up, and you'll be able to talk to the speaker personally after the talk. So, are we ready for questions for Kevin?
So how do we know that the yellow galaxies aren't just a redshift effect? How do we know that they're really red and dead?
Oh, that's an interesting question. So the redshift actually comes from the spectra that we obtained. So the original Sloan survey gives us a spectrum that has really sharp lines in it, and so we know where those lines ought to be, and that helps us measure the redshift. And then what we're talking about in the color is more of the broadband spectral shape. So we know the redshift from the spectrum. The color comes from looking at different images in different wave bands.
All right, I thought black holes had so much gravity that nothing, not even light, could escape. How is gas coming out?
So that's a good question. I sort of referred to that tongue-in-cheek. So black holes can blow out gas as well. And what happens is material comes in, because it's attracted by the gravitational force of the black hole, and it starts to orbit around the black hole. And as it does so, it's releasing the gravitational energy that it picked up as it was falling in. It makes that material very hot, and that hot material can actually launch jets, outflows, and the kind of phenomenon that we think we're seeing.
And then, are these black holes in every galaxy, or just some?
I think the jury is still out on that, but we believe they're in nearly every galaxy, and certainly above some size or mass limit, you would definitely expect to see, or you would expect to have a black hole. It's an open question as to how small a galaxy may or may not have a black hole.
All right. What is the material being ejected in the outflows from dead and dying galaxies?
So we don't actually know the answer to that. We've seen a part of it. We've seen one phase of it. We know that it's hot ionized gas is at least one component. But there may be more going on. And so we're actually following up with other observations to try to figure out what the constituents are in that material. That'll be important to find out.
So I think that's good. I think that's great. Thank you so much for your questions.
Thank you, Kevin. Okay, so it is time to get out your raffle tickets, which you should have received at the entrance. We'll be giving away 4 of our universe-famous Astronomy on Tap beer glasses. So get your raffle tickets out. I'd also like to ask Kevin and Tim to come back on stage. You're going to pick our winners here. So take a look at the number on your ticket, and we're going to start with Tim. He's going to pick our first winner.
Okay, so 39460.
460. Anybody?
Anyone with a ticket ending with 460 here, please let us know
Make a
and
noise.
come up stage to get your beer glass. If you don't, we'll give it to someone else.
Wave. Oh, yeah.
Is there here 460? Yes. Okay. Congratulations. Okay, next one. Kevin.
Okay, I have 39403. 403.
403.
403, are you here?
Wave your
Please
arms. Do something.
let us know.
Look there. Yeah, right here.
Okay.
Great.
Excellent. 2 more to go. Curtis.
All right. 039459. 459?
459 here. Yes?
Yes.
Okay.
Yes. Excellent. Great.
Here we go. Okay, last one.
Last one.
Here we go. Zero three nine 419.
Hey, right up front. Great.
Oh, right here. Nice. Okay, we'd like to thank our 2 excellent speakers again. We'd like to thank the Matrix for hosting us and Las Cumbres Observatory for supporting us. And we'd like to remind you, please, if you have 5 minutes, either scan this code with your phone, go to that website, and please tell us who you are anonymously. And thank you very much for coming. Our next event will be June 14th, and we look forward to seeing you all there. Thank you very much.
Thank you.